Hello, my name is Kason Markley with the University of Illinois at Springfield, and today we'll be finding the structure of an unknown substance using mass spectroscopy, infrared spectroscopy, proton NMR, and carbon-13 NMR. Now the structure we'll be using today is C10H7Br. Now first off, with our mass spectroscopy, the first thing you want to do is find your M plus peak, which corresponds to the molecular mass of your structure. And so for us, our M plus peak is going to be at 206. Next, you want to find your base peak, which is also your most stable peak. And for us, again, it's going to be at 206. Next, you want to see if you have any useful fragments that'll help you figure out what else might be in your structure. Now for us, there's nothing particularly helpful, but from our formula, we do know that there is one bromine, but there are no other halogens, and that we have no nitrogens. Next, you want to determine what your degrees of unsaturation are. Now that's found by taking the number of carbons you have, in our case 10, multiplying it by 2, adding in the number of halogens, which we have 1 bromine, and then subtracting the number of hydrogens, which we have 7, and dividing all of that by 2. Now when you do that, you get a number of 8, which suggests that you either have 2 benzene rings or that you have a ring in some combination. Since we have so few carbons, it's highly unlikely that we have 8 double bonds. Now with infrared spectroscopy, we're going to analyze each of the 5 different zones. So in zone 1, which is your proton to other functional groups, you'll see that there's pretty much no signals at all. And so that means you're not going to have any alcohols or carboxylic acids or anything containing nitrogen. Next, if you look in zone 2, which is your carbon-hydrogen sp3 hybridized, you'll see that again we have a little bit of a signal, but there's not really a whole lot to be concerned with there. So we're going to act as if there's nothing. In zone 3, which is your carbon-carbon triple bonds, you'll see that again we have a tiny blip of a signal, but it's nothing really to get worked up about. In zone 4, which is your carbonyl groups, you'll see that again, really nothing to be concerned about. And then in zone 5, which is your carbon-carbon double bonds, here we finally have a spike worth noting. So that means we either have just some double bonds, or this contributes to our idea of having 2 rings. Now, normally in the fingerprint region, we would ignore everything in there, but since there's quite a few spikes that are being noted, this would suggest that we have some aromatic tendencies going on. Now, first off, in Proton NMR, you want to find the number of environments you have. In our case, we have 6 environments. Then next, you want to try and assign those environments to a functional group. All our groups are aromatic because they all lie between 6.0 and 8.5 parts per million. Next, you want to take note of the fact that we have 2 unusual splitting patterns. One forms a doublet of triplets, and one forms a doublet of doublets. Both of these are caused by benzene. So again, this is moving more towards our idea that benzene rings are forming our DOI. Now, because of this, our N-1 rule does not work. So that means we can't use the number of peaks to determine how many neighbors there are to each proton. Finally, in carbon-13 NMR, we're going to do basically the same as what we did in proton NMR, but instead for carbon-13 isotopes. First, you'll note that we have 9 environments in this one, but that again, they're all aromatic, falling between 100 and about 155 parts per million. Really, that's all carbon-13 is going to be able to tell us for now. So now we're going to go ahead and just compile what we've learned thus far. So from mass spectroscopy, we learned that our formula was C10H7Br. Our M plus peak was 206. Our base peak was also 206. Our degrees of unsaturation were 8, which was suggested that we had either 2 benzene rings or a combination of rings and double bonds. We learned there weren't any useful fragments, but that we did have 1 bromine and no nitrogens. From infrared spectroscopy, we learned that in zone 1 we had no alcohols, carboxylic acids, or nitro groups. In zone 2, we learned that we didn't have any carbon-hydrogen sp3 hybridized. In zone 3, we learned that we didn't have any alkynes. Zone 4, we had no carbonyls. In zone 5, we saw that there were carbon-carbon double bonds present, which could be aromatic or could be just regular pi bonds. And in our fingerprint, we saw that we had a little bit of aromatic tendency. Now from proton NMR, we learned that we had 6 proton environments, all of which were aromatic. And we saw a couple of splitting patterns that were very consistent with benzene. And from carbon-13 NMR, all we really learned was that we had 9 environments, all of which were aromatic. Now we can start trying to build our structure. So the first thing we're going to want to note is that everything points to benzene. If you remember, our degrees of unsaturation were 8, which meant that we most likely had 2 benzene rings. Our proton NMR and carbon-13 NMR environments were all aromatic, and we had a lot of aromatic tendencies from our IR fingerprints. Now, the big question is how we're going to orient these rings. Well, if we were to have the 2 rings be separated, it would take 12 carbons. But from our formula, we know that we only have 10 available. Therefore, the only way that they can be situated is they have to share a side. Now, this structure is shown in the front there by naphthalene. We're going to use this to build the rest of our structure. Now, as I'm sure you've noticed, naphthalene is a very symmetrical structure. Theoretically, there should only be a few environments for protons and for carbons. So it means that the placement of the bromine is going to give us all those extra environments. Now, the big question is, though, where is that bromine? Now, if you'll remember, halogens and aromatics de-shield protons and carbon-13 isotopes by drawing away electron density or delocalizing it. Now, in our proton NMR showed that we had one proton that was much further downfield than the rest. And so what this likely means is that that proton is probably caught between the halogen and the shared benzene ring side, which is going to have an increased aromatic effect. So this is shown by the structure 2-bromo-naphthalene. Now I do want to point out that technically you could put the bromine on any of the 4 spots denoted by blue arrows and it would still be the same structure. So now we're going to see if this structure holds up against our environments. First, we're going to test this out against our proton environments. Now remember that the placement of the bromine and the fact that we have a ring merger will affect our electron density. I've shown this in green. The bromine's inductive effect is going to pull some electron density away, but the resonance effect of both of our benzenes merging in the center is going to be much, much stronger. It's going to delocalize these electrons very heavily. So our first proton is going to be located between the merger and the bromine. And as you can see, the electron density is being pulled away by both effects, which is why our proton is so far downfield. Now, para to that proton is going to be our second proton. As you can see, it's just as close to the merger as the first one, but now it has an additional carbon between it and the bromine. So its downfield shift is going to be a little bit shorter. Now, a trans across the merger will be our third proton. As you can see, the fact that it's trans to the previous one is going to give us that characteristic benzene split. Para to that proton is our fourth proton, which is just a little bit less chemically shifted because even though it's the same distance from the merger, it's a little bit further away from the bromine and so is barely being affected at this point. Now our fifth proton is actually next to the bromine. Now as you can see, this is the first proton to be 2 carbons away from our merger. And so the resonance effect on this proton is much smaller compared to the other ones. So even though it's closer to the bromine, it's actually still having less of its electron density pulled away. And then finally, our 2 remaining protons belong to our sixth environment, because as you can see, there's still 2 carbons away from our merge point, like our fifth proton, but now they're so far away from the bromine that it's basically completely unaffecting them. And so in short, yes, this does fit our proton environments. Finally, we're going to compare our structure to our carbon-13 environments. Now remember again that the placement of the bromine and our ring merger will affect our electron density the same way it did our proton environments. But one thing we do need to keep in mind is that now we actually have carbons directly on the merger. And because of this, the resonance effect is going to be exceptionally strong, sending our carbons very far downfield. And so that's why you'll see our first and second carbons are both directly on our merger with only slight differences due to their distance from the bromine. Our third carbon is going to be directly between our bromine and our merger. The inductive effect of the bromine is not as strong as the resonance effect, but it is still enough to send it further downfield. Our fourth carbon is going to be directly across from that. It's the same distance as our third carbon from the merger, but is now one carbon further away from our bromine, so the inductive effect is a little less strong. Directly trans from our fourth carbon is our fifth carbon, and because of this, it's the same distance from our merger, but is further from the bromine, so it has very little inductive effect going on. Our sixth carbon is directly across from our fifth carbon, and at this point it's so far away from the bromine that it's having next to no effect, but is still close enough to the merger to be having a strong resonance effect. Our seventh carbon, which is directly attached to the bromine, has the strongest inductive effect, but is now 2 carbons away from our merger, and so has a much smaller resonance effect when compared to the rest of our carbons. Our eighth carbon is directly next to our seventh carbon. Again, it is further away from the merge point, but now is also 1 carbon further away from our bromine, which reduces both the resonance and the inductive effect. Then finally, our 9 carbons are the only 2 carbons remaining, which are the furthest away from our bromine, which means that they are having 0 inductive effect, but are still having a little bit of a resonance effect. So in short, yes, our carbon-13 environments also match our structure. And so our structure is indeed 2-bromonaphthalene, and that's how you use mass spectroscopy, infrared spectroscopy, proton NMR, and carbon-13 NMR to analyze the structure of an unknown substance.